This is exercise number 20 for the TC Lab in the process control class. We're going to be doing second order regression where we fit a second order model as the data arrives. If you'd like to follow along, here's the link, and it has all of the source code that we're going to be using today with a couple tips on getting your model implemented and then a solution down below that we'll take a look at as well. All right, so we want to develop an adaptive regression, one that figures out the parameters as it goes, not necessarily waiting until after all of the data is collected. We're going to use a second order model for this. So instead of a first order plus dead time, we'll just use a second order model and see how well it can fit to the data. Now, you have practices like gain scheduling or others that change the controllers as they go. You may have something like if you're in a region of operation, you're going to use one particular gain, and if you're in another region, you might use a different one. You also might segregate the gain of the controller by how far away you are from the set point, or there are other methods for changing the gain. So this is going to be an adaptive regression. We're going to be able to estimate the gain and the other parameters. So we just want you to think about how could this adaptive parameter regression be used to adapt a PID controller with gain scheduling. Alright, so if we just jump right into it, we're going to solve the adaptive parameter regression with either the SciPy minimize or Python Gecko. We'll modify the function to include the analytic solution for the overdamped second order response. So we're going to modify this section of code right here to fill in the t-value and be able to give us the model solution based on those parameters. Okay, so we don't want to use something like odint. We want to be able to just put an analytical solution in there so it calculates very fast. All right, I'm going to go through some of the code. And let's just build this just line by line. We're going to import TC Lab because we need to get the connection to the data. We'll import NumPy, time, and we'll also have a plot that generates as well. We'll do SciPy optimize minimize, and then random. We're going to use that just to give us some, so the optimizer doesn't get stuck. All right, we have a second order model with some of the parameters, KP, tau s, and zeta. Now, if you go back to the course website, you can see more information on second order systems right here in the menu. And so these are the parameters that we're going to be estimating, the tau s, zeta, and KP. And we won't have any theta p in this one. All right, let's go back. All right, we're going to detect if the session is IPython or not, so you can run this in IPython notebook. So we'll try to get some of these parameters. If it's not IPython, it'll return an error, and do this instead, say IPython is false. Okay, we'll have our magnitude of 80. We're going to go from 0 to 80 for our heater value, and then we'll have our second order step response. Okay, so I'm just going to leave a question mark there. In fact, let me just make this just a little bit bigger in terms of the text for the code so you can see it. All right, we're going to fill this in just a little bit later, but we'll return y from this model prediction based on the y naught, which is our initial condition, t, m, kp, tau s, and zeta. We're going to be able to return what the value of y is. Alright, now we need to define an objective for the optimizer. This needs to be a sum of squared error or sum of absolute errors. We're going to use sum of squared errors for this case. Here is the p that came into our system, and we're going to split that out in terms of kp, tau s, and zeta. And then we're going to just create, get the number of time points, create the y prediction. Okay, so that's going to be the number of ones times the initial condition, and then we'll update that. We'll call our model over and over again for every time point in the horizon with those parameter values that we had, the 3. And then we'll calculate our sum of squared errors, and then we'll penalize some bound violations. So we could use some options for scipy.optimize.minimize that have bounds, or we put in soft penalties there to discourage it from going away from outside of that bound. So 10 to 200, 1.1 to 5 for zeta, and then for KP it's going to be between 2 and 0.5. So if it's outside of that range, we're going to hit it with a pretty hard penalty and tell the optimizer to stay within those bounds. Then we'll return the sum of squared errors. Alright, now we're going to connect to the TC lab, print the version of the lab, turn on the LED, and then we'll have a 5-minute runtime. We're going to go for 300 cycles, and then we'll get our current temperature for the measured and predicted values. We'll just initialize those with measured values first of all, and then we'll do a step test with the magnitude M equal to 80. Then we'll run. If you want to end it, you can just do Control C. I don't think that works in a Jupyter Notebook. I think you just have to restart the kernel. Alright, so we're going to create a plot. If it's not IPython, we're going to use interactive on and show, and then have our main loop. Okay, so here's our 300. Here are 300 loops. We're going to have a sleep time of 1 second, and then we'll record the time and change in time. So this just helps us automate the cycling every 1 second and recording the time. Then we'll read the temperature in Kelvin, and here's our estimator. So we're going to estimate the new parameters every 3 new data points and wait until we get beyond 15 seconds, just so we have some data. We'll randomize a little bit the guess values just so we don't get stuck in a local minimum. It's going to be searching, it's going to move it away from the prior optimal value. Okay, and then we're going to minimize. This is the minimize function from scipy.optimize. And we're going to use our objective function that we had with our initial guess value for the p values, and then we'll have our time values. Alright, then we'll retrieve our solution once it's all done, and then get the KP, tau s, and zeta. I just put a max and min on the tau s and zeta just so it doesn't go outside of that range. Then we'll update the second order prediction by looping through all of the time points that we had measurements for, and then we'll write the new output. That should just be 80, and then we'll print the header every 15 cycles using the modulus function, and then print the data each cycle. Alright, here's our plot. I'm going to go a little bit fast through this. We're just plotting our measurement and prediction and adding some labels and Q1 down below in the second subplot. Alright, so at the very end we're going to turn off the heaters, save the figure, allow the user to end with Control C. So there's a keyboard interrupt, and then all of their errors is going to catch it and turn off the heaters. Alright, let's go back up here to our output of the model, and we want to fill this in with the analytic solution of the second order overdamped system. So that's going to be, if you come back to the course website, here are second order systems, and this just shows the overdamped analytic solution right here. So I'm just going to put this off to the side just as we work on this. Okay, so let's go ahead and just create y equals kp, and then I'm going to add some other things. I got to add back in that y naught because it's all in deviation variable form. I'll have the m, and then I'll multiply by 1, and then let me make some helper functions here because I use some things over and over again. I'm just going to call this a, and I'll do minus zeta times t divided by tau s, and then I'll put in a right here. So it's just going to simplify my expression because I'm going to use that. I don't want to make this expression too long. Alright, and then I'll have a times, let's see, zeta, let me go ahead and just add b here as well. I'll have zeta squared minus 1. That's going to be the what goes inside the square root. Alright, and then I'll have zeta divided by b. Alright, let me just go ahead and keep building this. And this is just going to, I think, wrap around a little bit. Let me go ahead and fit this all here on the side. Alright, I'll move this over. Oh, it looks like it doesn't want to move. Okay, there we go. Alright, just keep building this. I'm going to add a c, t divided by tau s times b, and then just put in the hyperbolic cosine of c, and then the hyperbolic sine of c as well. Alright, so there I go. I have my analytic solution there, so every time point I can calculate what the predicted value is based on those three parameters. Let's just run this, and then we can work on the other one in just a second. I'm going to run this here with IDLE, Python 3.7, but you can also run it through Jupyter Notebook. Alright, so when it's going to connect to the Arduino and then start, what we're going to do is it'll bring up a figure, and then we're going to see the data and our prediction, and it hasn't started to estimate any of the parameters yet. It's just using the default ones until it gets to 15 seconds, and then it's going to try to adjust some of these parameters. Okay, so here's our first one. It started adjusting, and you can see the KP, tau s, and zeta that are being estimated, and you can see those values changing. It's lowering the gain a little bit, try to bring it in line with some of the other values that are there, the measurements, and you can see that you know, all of those are adjusting. You can see it kind of snapped into place. The optimizer found a better solution by adjusting those parameters. Every time it's searching, trying to find something, it'll minimize the sum of squared errors between all of those data points. Every one of those dots that you see, it's comparing it to the model prediction and then trying to minimize that. So it's trying to do that for all of these, and as you get 3 new data points, then it re-estimates the values. Alright, so you can see every third cycle it's going to change the value slightly as it tries to minimize that some of the squared errors. So it's you know, about 0.56. You can see the tau s value and then the zeta value. I'll go ahead and pause this in just a little bit. We're going to just watch and how this does. Okay, it's under predicting right now. The gain is a little bit too low, but we'll see if it's able to fix that. Okay, just one note of caution is the SciPy .optimize.minimize solver is not the best solver that's out there, so sometimes it finds you know, gives up after a certain number of iterations, doesn't quite find the solution. I'll show you the Gecko, Python Gecko, in just a little bit and see how that one does. Okay, it's about 200 seconds into it now. You can see the gain here on the second column. You can see that's calculating and estimating the gain. Now, one of the things that we could do is make the controller gain a function of this KP value that is estimated. Now, most people don't like to do that because they want to know exactly what their controller gain is, and they don't want some other application like an optimizer changing that for them. But that is a possibility. You could have adaptive control based on these parameters that you're estimating in real time. One of the dangers is if you don't have sufficient variation in your controller output or your system input, then you may not have enough information in order to be able to estimate the second order model. So it's going to continue. I think this actually goes for 5 minutes. Let me just check this. You know, I think I said 4 minutes in here, but I think it was actually, yeah, 5 minutes. Oh yeah, 5 minutes right here that we're going for. Okay, so it's almost done, maybe about 30 more seconds. And it looks like it's doing a fairly good job. You can see the black line is right in the middle of these dots, just a little bit low up here. But overall, it's doing a very good job of estimating those 3 parameters. Alright, so let's see, it should, okay, there it goes, it just finished. Alright, so let's do Python Gecko now. That's the second solution that's there, available for download. If you come back to the assignment page, alright, there's also this one, the second order adaptive regression. Okay, same thing as before, you just have to fill in this part of the code right here. And again, if you want to get this, just go down to the bottom, don't just copy it, use the get code link right there and it'll give it to you in raw format. Alright, now if you don't have the Gecko package, you can always get that. Just go to the command window and you can do pip install Gecko, and if you already have it and you want to upgrade it, you can just do the -- upgrade. Okay, and if you don't have administrative privileges, you can do the -- user, and then that will just install it locally for you. Alright, so I'm going to come back here. Let's just open up this other one and then just walk through the parts of it that are related to Gecko, and then we'll just run it again and see if we can get similar results using a different optimizer than SciPy optimize minimize. Alright, okay, let's see. I'm going to go through here and just first of all just create a new Gecko model with FVs. These are fixed values that are the same value over all of the time points, and we have KP, tau s, and zeta. And we'll add a lower bound and an upper bound. In terms of KP, that'll be between 0.5 and 2 with an initial guess of 1, and then tau s will be between 100 and 200, and zeta is between 1.1 and 5. Alright, and then we have our initial value for y. We're going to use y and u for this. Okay, u is our input and y is our output. And then we'll create a new variable x and y. Now x is going to be a variable, and then y will be a controlled variable, or CV. And that is so we can put an objective function in there for its measurement. And then we'll create our first equation, which is x equals the derivative of y. So x is going to be our used to get our second derivative. Okay, we have tau s squared times dx dt. That's the x dot dt open and close parentheses. And then we'll have our second term, which is 2 times zeta times tau s times dy dt. And then we'll add in y minus y naught. And the reason why is because that's a deviation variable. And then we'll have kp times u. And it should be a deviation variable for u as well, but you start at 0 for the heater value. Alright, we're going to change it to I mode 5, which is moving horizon estimation or dynamic estimation. Default is 2 anyway, so I could have left that one out. There are my time points. I'm going to estimate new parameters every 2 seconds. In the prior script, it was every 3 seconds. And then we'll solve it. We'll just turn display off so we don't have to see it. Okay, F status, that's the feedback status for Y. It means that we have a measurement available. We want to try to match that up with our model value, measurement model together. Alright, let me come down here. I'll make this just a little bit wider. Okay, so now what we want to do is just do the regression with Gecko. This is going to be our main loop. And we'll just say if I equals 5. Okay, so 10 seconds into it, because we run every 2 seconds, We're going to turn the status on for all of these parameters so it starts to estimate these. And then we're going to insert our measurement for the U and Y, being the Q1 and the T1. Q1 is just going to be 80, and then T1 is going to be coming from line 101. There's our measurement right there. Okay, and then we want to solve it. We're going to solve the Gecko model, and let's just come back up here and insert this model in here. This is just to be able to provide the plot, okay, just like we had before with the A, B, and C, and then we just construct this based on the analytics solution, and there is our test number 2. This is going to be with Gecko instead of the SciPy optimize minimize, and I'll just run this with, again, ideally. Alright, and I switched out the top just while I was talking, so it should be cool, and it should start at about room temperature. Okay, there it goes. So it's going to wait 10 seconds before it's going to start estimating the parameters, and then it will start to adjust those. You can see it dropped the gain, and it looks like something's happening with this. It's not heating up very much. Okay, there it goes. The data is starting to increase, and you can see the it's starting to adjust the KP, tau s, and zeta value. Now zeta value is at the lower bound. Okay, so it's saying that we want to even go lower than it allows us, and it's at a constraint, so that may be why it's not matching up right now, because we have a bound on that, and it wants to move it past that bound in order to match it even better. Okay, so we'll let this one go for a little while as well, and just see how it does with the Gecko version of this instead of the SciPy optimize minimize package. Okay, so we're about 170 seconds into it right now. You can see the gain is about 0.95, tau s is 64, and then the zeta value is 1.52. So as we got additional data, it was able to fit it better and had more information, so I was able to come up with better parameters. Okay, so it is this one is also heating up just a little bit more than the other one. I just changed the shields on it, so they're slightly different. Every TC Lab device is going to be different and give just slightly different data as well. Okay, so I'll just end here. I won't let this go all the way to completion. It'll go for about another 50 seconds or so. The next tutorial is going to be on higher order systems. So we're going to do a third order system, matching up the dynamic response between heater 1 and temperature 2.